Hi there, and welcome back to Advanced SQL Chapter 6, our discussion of recursion in SQL. Right, now that we have k-means clustering in our bags and have briefly touched the area of data analysis and machine learning, let's switch gears altogether and look at the quite different area of algorithm and problem again. This would be motivated by computer graphics. So what we'll be looking at is the marching squares algorithm. And well, this has its origins in the, computer graphics. So quite the broad coverage of areas that we can touch in this chapter of the course. Why I bring up this particular example in the course is also for a different reason. It's an exposition or an example of a technique that I find quite efficient and quite interesting in the context of a database system. And it's about the encoding of logic or of control flow. So what will an algorithm do next given the current state? What's the next step to take? Such control flow can of course be implemented in regular programming languages using if then else's and conditionals in general. But in the context of a database system, well, we have our own means to implement decisions or control flow. Of course, we have the where and the having clauses, which take predicates that we can evaluate to decide whether a particular row is to be included or excluded from a query result. So that would be some form of control flow. There is one form of control flow that might not be that obvious, and that would be the union operator, right? So we could have a group of queries, Q1 to Qn, as they are called here on the slide, and they could represent the different branches of a computation that we would like to perform. The separate queries, the QI here, they would contain guard. They would contain predicates that control whether QI is allowed to contribute rows to the overall result. So a branch of the computation that is currently not being selected would probably contain a guard or a predicate that evaluates to false. So QI would not contribute to the overall result. Other branches, maybe more than one other branch, may indeed contribute, and thus this implements a different form of branching and control flow inside a system that is actually being designed to perform set-based computation. Right. Of course, there's also the conditionals that you know and love from the regular programming languages. So instead of if then else, we would have the multi-way conditional, the case P, when then, when else branch construct, which operates on the expression level, not on the table level, just like this second entry in the list here. So that would be a regular conditional expression that we can evaluate, and this is also at our disposal. And then there is one other way, a more data-oriented way to implement control flow in query. And this is actually a technique where we actually turn control flow into data flow. Right. So what we will do is we encode query logic or a decision by an algorithm using the rows of a particular table. Okay. So that table will have a mapping from a current state of the system, okay, to a decision that is to be performed in this particular state. If there are many possible states and many possible decisions, this would only lead to more entries in that decision table. It would not lead to a change in the query code, so not a new branch in a case, not a new entry in this list of union all, not a new predicate or maybe a new AND or clause in these predicates P here. All of this, the query would remain unchanged. We would just insert more rows that encode our decision in terms of data into these decision tables. I think this is a very powerful technique, and well, it comes up in the context of marching squares. So let's look at marching squares here. All right, so as I told you, this is an algorithm from computer graphics, and it's being used to isolate shapes, or it can be used to isolate shapes that are located in some space. So again, we are looking at slides here, and this is all two-dimensional. So what we will be looking at is some pixel-based graphics. All right, so that might be our entire graphics. And as you can see, on the canvas of our graphics terminal, there is an object, the dark object that I've outlined here. We would like to trace the plan and find the contour, the edges of this particular shape. So we would try to perform a walk around this shape in this fashion. So to trace the border of the shape to find the actual shape on the 2D plane, then extract all the pixels that are part of the shape and then have them whatever subject to some further processing. Maybe we could just cut this particular shape from its environment and then process it separately. All kinds of cool stuff could be done. What we are concerned with is the marching squares algorithm, which indeed performs such a trace around the border, or around the boundary or the border of an object in the graphics plane. Okay, right. So, well, the algorithm that we will pursue is quite simple. We will look at this plane, right, and we will look at one square of pixels at a time, right? So let me identify the first square of pixels that we will look at. It's this 4 by 4 square of pixels. I hope you can see that here in the video. It's this 2 by 2 square of square of pixels. So that would be 1 pixel inside that square, and there's the second pixel, and the 2 pixels on the right here, they are black, while this is background or white or whatever, what have you. So that would be the 4 pixels that we are looking at this particular point in time. I have also highlighted the current square of pixels that we are looking at here in these following states of our algorithm using this mid-gray tone here. All right, so that would be the current group of pixels we are looking at. And well, that would be part of the boundary, of course, but where to move next? Where would we move next? Well, we will move in counterclockwise orientation around our shape. So we would try to move like this. So given our current position at the boundary of the shape, where would we move next? Well, of course, it depends on the pattern of pixels that we currently see in this 2 by 2 square. Given this particular pattern of pixels, well, we could decide where to move next. So in this particular situation, the algorithm would decide to move our square of pixels down to perform a trace downwards, which probably would then at one point turn right to follow the boundary of the shape. The decision to move downwards in this particular state is encoded in a table. It could be encoded in whatever 16-way, multi-way conditional expression, but we won't do that here. We will use a table. The one thing that our systems, our relational database systems, are built to cope with and are experts to cope with. So that would be that table. This table would be used to decide where to move our square of pixels next. So the current state says that on the left there is 2 background pixels and on the right there is 2 black pixels. We would look that up. We would look that up in this table of that contains a mapping from the current state of the 2 by 2 square of pixels. I have found the current state here. On the left there is 2 white pixels, on the right there is 2 black pixels, and the table says in this state move downwards. And that's what we are doing with our square. You see, from state 2 to state 3, we have indeed moved downwards with our square, and it's here now. While we move the square, we will keep a record of its center point, because its center point will then later define the points of the boundary of the black object. Okay, so we've moved down now, and the next decision to make is where to move next. So we would just look at the state of the current square of pixels, 3 white pixels on the lower left and 1 black pixel in the top right. And I think this would be this state here. Okay, so 3 white pixels in the bottom left and 1 black pixel in the top right. Okay, so move right now. Okay, and that's what we do. We have moved our square of pixels to the right. And okay, let me draw this a bit more carefully here. All right, so this way. Okay, so that would be the next state. And so on and so on. So let's trace one more. White pixel on the bottom left, everything else black. This is this state. All right, so all black pixels but the bottom left move downwards. All right, and that's what we do here. As you can see, we've moved downwards with our square, and we would just move around this shape in this particular fashion. Would always check the current state of the square, would perform the lookup here. All of the cases that we can find in this lookup table, actually there are 4 pixels inside the square. Each of the pixels can be set or can be unset. That leads to 2 to the power 4, 16 entries in our table that decides the movement. Right, there's one particular entry that indicates that we are in the midst of the shape. So we are not at the boundary, but in the midst of the shape, and all of the pixels are set. This would be considered an illegal configuration, and the algorithm would stop at this particular point. Okay, so all of these movements, all the other 15 entries that you see in this table will make sure that we indeed trace the boundary of the shape and will not enter the shape itself. All right, so I'd rather use this encoding of the marching squares algorithm in table form than having my queries cluttered with 15 or 16-way multi-way branches that are tough to read, tough to modify, tough to explain, and tough to maintain. All right, so I think all the ingredients are already there. So we could formulate a query plan. How would we indeed implement this particular algorithm? Well, of course, one very important thing is the encoding of our table of directions, where to move next. So, and what this table would do, it would map a 2x2 square of pixels to a direction in which to move. And a direction in which to move, in this case, we are either moving left, right, up or down. So we could easily move that, encode that direction to move in using delta x and delta y values that are either -1, 0, or 1. So a movement of 0 means stay where you are. A movement of -1 or 1 means move left or right or move down or up. Okay, so that would be the encoding of direction that we are using, and this table directions would then simply map such a square of 4 pixels into a direction, which is just such a 2-tuple of delta x and delta y values. In this case, it would mean to move rightwards. This would encode a movement upwards, which you can find here. I think that's simple enough. This table directions will have entries for all of the possible 2x2 square map patterns that pixel patterns that we can find. Before we perform the merge itself, which of course will be the iterated or the recursive part of the query, we will do some processing on our pixel grid, and from our pixel grid, we will derive a table squares in which it is easy to check for one particular pixel what is the state of the pixels in the immediate vicinity. Right, so we would for each pixel inside our pixel plane, inside our canvas, we would record the state of the pixels to the right and below and to the upper right, and that would be the form a 2x2 square pixel map, which we will then store in a table squares. This is just for convenience, so that it's super easy for us to check the state of the pixel around our pixel P0. Once we have these preparations, tables directions and table squares, it's easy to perform our recursive CTE. It's actually so easy that we can describe it here on the bottom third of the slide. Well, we would just have a base case query that starts us somewhere in the plane, right? Of course, our goal is to record all the XY coordinates of the boundary of the object in the plane, and this is exactly the goal of our recursive common table expression, to compute a table march that contains the XY coordinates of the boundaries of the shape. Q0 would simply enter this particular coordinate into this table. We are locating ourselves somewhere on the plane, somewhere to the left of our object, which is where we would start our march, right? So we would then approach the object from the right, until we hit the object. So the setup will be this. We will start at position 1, 1. We will then move to the right until we hit the object. Let me draw the object here. And then move counterclockwise around the shape using our directions table, the marching squares algorithm, until we hit the first point that we have hit on the boundary again, and that would mark the end of the algorithm. All right, so we have to make sure that our directions table moves us to the right whenever we start anywhere in the pixel plane where there is no object to be found. And you will see that there will be one such entry in our directions table. Okay, right. And then in the iterated part of the query, well, we would just look at our the current position, the last position that we have reached in during our march. That would be one XY position. That XY position would be looked up in the squares table. Now we've got information about the neighboring pixels, the state of the pixels in the vicinity of XY. And we would use the state of these pixels of XY and the 3 pixels in the vicinity to perform a lookup in directions, because directions will tell us, given that this is the state of the pixels in your vicinity, delta X and delta Y is the direction you should be moving in. So that's what we are doing. We are currently at XY. Directions table tells us to move into the delta X, delta Y direction. That's what we do. This will be the new pixel of the new location of the next step in our march around the object. Done. Okay, this is easily expressed in SQL, and that's what you see here. As I told you, the base case query will start off our 2-column march table with just 2 entries, 1 and 1 here. And that's all about it. This is the base case query Q0. You see that it produces a result that fits the schema of our march table, which just records the coordinates of our shape boundary. All right. So now in the recursive part of the query, this would be the recursive part of the query. We would look at the last position that we have reached in our march, and let's call that position M. We would perform a lookup for this position M inside our squares tables of 4x4 pixel neighborhoods. And you can see that this lookup is being performed using this comparison here. Comparison of our position M with the position of inside the squares table. Done that. Okay. All we need now is access to the direction table, because it will tell us, given the current squares state, given the current vicinity of our pixel, where to move next. So we would use the information in the squares table. This is actually the information found in the squares table about our pixel itself in the lower left corner, in the lower right corner, in the upper left and upper right corners of this 2x2 pixel square. We will perform a lookup for this particular pixel pattern in the directions table. and we would find a direction there. d.dir is the direction that is associated with the current pixel pattern. Okay, so this direction has a delta x and a delta y part. We would use these to add to our current position, to the current position that we have reached in our march, and that would define the new position that we have reached during our march. And it's exactly this new position that we add to the iterated table as the next pixel on the boundary. And that's all about it. As you can see, I'm using lateral here, lateral and this values clause. Well, this is just for convenience. As you can see, this values table, this literal table computes a 2-column table of a single row. It's just the new x and y coordinates of our march, and I'm using them above here. This is just for convenience. It's just a matter of style. It's just like a let in a function programming language. So let new x this value, let new y this value, and then we can use new x and new y in the rest of our query. It's only one time up here, but right. So that's it. That's about it. This is the marching square SQL code, and you can see the cool table lookup here. This table lookup saves us from encoding a 15-fold case distinction using, for example, case whens or unions or whatever you like. All right, time to switch over to the terminal. And so you can see that all of this is indeed working. So first we've got an input table here that encodes the 2D graphical plane and the object on that plane in a fashion that we can easily edit, change, and play with. So let's generate this table, and you can see what I mean by an easily editable and changeable representation. That would be the 2-dimensional representation of our plane. Here is the object that we are defining. So it's just light and dark gray pixels or characters on this plane. Let's copy this into the input. 7 rows. All right, let's see, what have we got here? Yes, well, we have seen such representations of 2-dimensional planes before. All right, so that would be the input. Let's scan this stuff. Let's scan the boundary of this object. Okay, we would convert this easily readable representation into a pixel map that has explicit x and y coordinates and stores the altitude or the height of the pixel at a particular position. So let's do that. This is a very simple 2-dimensional representation of this pixel grid. I'm just parsing the input, the line-based input here, and convert it into this XY based representation of 2D pixels. Done that. Let's look at the result here. All right, so you can see, well, indeed we have XY coordinates here, and for each XY coordinate we record the altitude or the color or what have you of the pixel at this particular XY position. Almost all of the pixels are at height 100 here, but there are some pixels that define the shape or lie inside the shape. You can see here, here's one of these pixels. These are the pixels that make up the object, and we try to trace the boundary of that object. All right, so what we need now is the directions table. So the encoding of which square configuration of pixels maps into what movement. And well, as I promised, this is being held in a table, a directions table that maps the state of pixels. These pixels are either set or unset, so we can encode them as booleans here to a direction. All right, so let's define that table and let's instantiate that table. As you can see, this is indeed the table that we have been talking about. Let's see, right, this is the state in which we are at the very beginning of the algorithm. When we are on the plane, there is no object inside. As I told you, in this state where there is no pixel set, so all pixels in the vicinity are indeed unset, we will move to the right. And that's exactly what we encode here in this table. Otherwise, we encode all the pixel configurations and movements that you've already seen on the slides. This is the illegal configuration that, is if we are inside the object, all of the pixels are set, then there is no movement that we could perform here. All right, so let's define that. And let's check. Well, yeah, this is just the expected table. This is the encoding of the algorithm itself, actually. So all of the decisions that are being made are encoded in these tables rows. Okay, so now let's define what the black pixel is. It's those pixels that are at altitude 200 as opposed to 100. Then let's define a black-white version of our pixel plane in which we check each of the pixels at each XY coordinate and then set this altitude column to true if we indeed hit a black pixel. All other pixels will be set to false. All right. This is what we've done with pixels here. And then the last bit of preparation, we will scan the pixel grid. Each pixel P0 will be the current pixel at one particular point. We will also scan for the pixels that are to the right of our pixel, or that are above our pixel, or that are at the top left of our pixel. Okay, all of these pixels are being collected from the 2D pixel plane, and their altitude or their pixel set and unset state is being recorded in columns upper right, upper left, lower right, as you can see here. And this leads to this information about the state of the pixels, the 4 pixels around these coordinates in the plane. All right, so this is the last bit of preparation, and now we could just perform the march. The march is so short that it fits in less than 10 lines. This is what I've shown you on the slides, and I think it's a verbatim copy of the stuff on the slides. And that's all there is to it. So let's see, let's first look at the pixels table. So it's not the output of the march, only at the pixels table. This is the table, the mapping of pixels, of individual pixels to their set or unset state. You see that almost all of the pixels in the plane are unset. Some pixels are set here because they're a part of the shape. So that would be the raw input that we operate over. We would then, from that individual pixel map, generate our squares table. In the squares table, I would find the vicinity information, the vicinity pixels around positions X, Y. There you go. So all of the pixels inside our square are now equipped with pixel information in their vicinity, in the lower left, lower right, upper left, upper right corners of these tiny 2x2 pixel squares. Well, and this is all we need to indeed perform the march. So let's perform the march. I think this is the last bit of query here. Here you can see we are indeed outputting the result of our recursive common table expression. What we do is, we shift the X and Y coordinates that we have recorded by half a unit here. So that we have recorded the lower left coordinate of the actual squares that we have traveled around the shape. To find the real coordinates at the boundary, we have to look at the middle of this particular square, and that would be done by these offset calculations here. But that's all there is to it. We could just dump the record. The record of our recursive common CTE and find this as the result. This would be the coordinates around the border of the traced shape. One final note, we are operating in set-based semantics here. Okay. And there is no notion of iteration or a length of a boundary that we've already traced, or some where clause that would stop us from performing more iterations in this recursive query. This is not needed if we can assume that we can indeed form a closed path around the traced shape. A closed path will at one point hit the first point at the boundary of the shape again. If you recall, I was drawing this particular circle around the shape on one of the slides. If we hit the first point at the boundary during our counterclockwise walk around the shape, well, then we reach a point that March has already seen. That would not be considered a new point on the shape. It indeed is not a new point. This would lead this particular query to not produce any new rows, no rows that we have seen before, and that would halt this recursion. It would halt the iteration, and we would be able to produce the final result and emit that to the application or the user. And that's all there is to it. This is marching squares that uses an encoding of control flow of how to move the current state of the algorithm by using such a decision table. Okay, so there is some more cool stuff up our sleeves and upcoming videos. I hope you will stick around. I think it's worth it. See you then. Bye bye.